All right, welcome to another deep dive here. Today we're taking a look at something that's absolutely essential if you're into virtual reality, video games, animation, anything that involves creating these really cool 3D models and worlds. We're talking about 3D mesh generation.
Absolutely, yeah. 3D mesh generation, it's like the backbone of so many things we see and interact with digitally these days.
Exactly. And to guide us through this complex world, we've got a fascinating research paper called DeepMesh.
Great paper.
Yeah, really interesting stuff. And of course, I've got my own notes and thoughts here, and I'm really eager to get your insights on all of this.
Happy to share.
So for our deep dive today, what I really want to focus on is the innovation behind DeepMesh. The more academic side of things, the stuff that makes it stand out from the crowd.
Yeah, that's where it gets really interesting, right? Like, how did they actually achieve these impressive results? What are the core technical ideas that make deep mesh so innovative?
Exactly. So let's start with the basics. I mean, when we talk about 3D models, what are the traditional ways of creating these meshes?
Well, you've got two main paths, right? On one hand, you have these incredibly skilled artists who basically sculpt and refine every single detail of a 3D model by hand.
Oh yeah, the digital Michelangelos.
Exactly, it's like a digital form of sculpting. And what they produce are these beautiful meshes with what we call optimized topology. It's all about how smoothly the surface flows, how well the triangles are connected so the model can bend and move naturally in an animation, for example.
Yeah, you can really tell the difference between a well-made, artist-crafted model and one that's, let's say, a bit rough around the edges.
Absolutely. But of course, this manual process, as beautiful as the results can be, it's incredibly time consuming. It takes a lot of expertise and a lot of patience.
Right. And that's where automated methods come into play, right? I mean, we have algorithms like marching cubes that can generate a mesh from, say, a 3D scan of a real-world object.
Exactly. You feed it to data and boom, you get a mesh. And the great thing about these methods is that they're incredibly accurate in terms of capturing the overall geometry.
Right, they get the shape right.
Yeah, but there's a trade-off. The topology, the underlying structure of those automatically generated meshes can be a bit of a mess.
A mess how?
Well, you often end up with these really dense meshes, tons and tons of triangles, and the connections between them can be pretty irregular, not very artist friendly.
Okay, so it's like you get the shape right, but the underlying structure isn't ideal for things like animation or further refinement.
Precisely. It can be quite challenging to work with those kinds of meshes.
And that's where deep mesh comes in, right? It's trying to bridge that gap between the accuracy of automated methods and the quality of artist-made meshes.
Exactly. Deep Mesh is all about saying, hey, can we get the best of both worlds? Can we automate this process, but still generate meshes that have that clean, artist-like topology?
And as we mentioned, we want to delve into the how. What are the key innovations, the academic insights that allowed them to achieve this? So where do we begin?
Well, the Deep Mesh paper really highlights two major challenges they wanted to overcome. The first one has to do with the pre-training process. So imagine you're training a model to generate 3D meshes, right?
Okay.
The first thing you got to do is convert that complex 3D mesh into something the model can understand, something like a sequence of discrete tokens, kind of like how we break down a sentence into individual words.
Makes sense.
But here's the catch. With these intricate 3D structures, these token sequences can become unbelievably long.
Oh, I see. So it becomes computationally very expensive to train a model on these massive sequences.
Exactly. And what would have been more interesting, they found that the quality of the training data itself can really mess things up. Like, if the model keeps encountering poorly structured meshes in the data, it kind of throws off the learning process, leading to instability and all sorts of headaches during training.
Right. So it's not just the length of the sequences, but also the quality, the cleanliness of the data that poses a challenge.
Precisely.
Okay, so challenge number one, pre-training woes. What's the second hurdle they were trying to jump over?
The second big issue was let's call it the artist gap. Existing automated methods could create a mesh that roughly matched the desired shape, but it often lacked that finesse, that refined structure that a human artist would bring to the table.
Yeah, je ne sais quoi, that artistic touch.
Exactly. And that's a problem, right? Because these automatically generated meshes would often have geometric imperfections, like little holes in the surface, disconnected parts, or just way too many tiny, unnecessary triangles cluttering things up.
Okay, so it's not just about getting the overall shape right. It's also about creating a mesh that's both structurally sound and aesthetically pleasing.
Absolutely. And that's a tough challenge for an algorithm.
So Deep Mesh sets out to tackle both these problems. Let's start with the pre-training challenge. They have this efficient pre-training strategy, as they call it. What's so special about it? What are the key innovations there?
All right, let's dive into that. One of the most important innovations is their novel tokenization algorithm. So remember how we talked about converting a 3D mesh into a sequence of tokens?
Yeah, the whole breaking it down into words analogy.
Right. Well, the standard approach, what they call the vanilla method, is pretty inefficient. It basically encodes the 3D coordinates of all three vertices for each triangle in the mesh.
Okay, so for every triangle, you list out the location of all three of its corners?
Exactly. And that leads to a ton of redundancy because neighboring triangles often share vertices. So you're essentially repeating information over and over again.
Right, like listing the same ingredients multiple times in different recipes. It seems like a lot of wasted space.
Precisely. And that's where DeepMesh's algorithm shines. They introduce this idea of local aware face traversal.
Local aware face traversal? That sounds pretty complex.
It is, but it's also really elegant. Instead of just processing the faces in a random order, they group them into these little local patches based on their connectivity.
Okay, so they're finding clusters of triangles that are connected together in a meaningful way.
Exactly. And by processing these patches together, they can significantly reduce redundancy because faces within a patch are very likely to share vertices. They even provide a nice visual illustration of this in Figure 9 of the paper.
Oh, cool. I'll have to check that out. So they're being smarter about how they break down the mesh into smaller units before tokenizing it. What else do they do to make this process more efficient?
Well, this is where it gets a bit more technical, but bear with me. They introduced something called hierarchical block indexing. Imagine you overlay the 3D space where the mesh lives with a grid, but not just one grid, a whole set of nested grids at different resolutions.
Okay, like zooming in and out on a map, you have different levels of detail.
That's a great analogy. They use three levels in their setup with block sizes of 4, 8, and 16.
Okay.
Now, instead of directly storing the XYZ coordinates of a vertex, they first quantize them. Basically, they round them to the nearest grid point at the appropriate resolution level.
So instead of saying a vertex is at like 10.2, 5.7, 3.1, they snap it to the nearest point on one of those grids?
Exactly. And then they store the location of that grid point as an index, an offset within the hierarchical block structure. There's a nice equation in the paper, equation 3, that shows how they mathematically transform the coordinates into these indices.
Okay, so it's like instead of storing the exact address of a house, you say it's the third house on the second block of the fifth neighborhood. It gives you a more structured way to represent location.
That's a cray way to put it. And because neighboring vertices tend to be close together, they often end up with similar or even identical indices within these blocks.
Right, so even more opportunities to reduce redundancy.
Exactly. And to squeeze out even more efficiency, they do this clever thing called index merging. If two adjacent vertices have the same offset index, they just combine them into a single representation in the sequence. Again, they give an example of this in equation 4.
So they're really going all out to compress this information as much as possible without losing the essential details.
Absolutely. And the results are pretty impressive. They achieve a 72% reduction in the length of the token sequences.
Wow, 72%. That's huge. I mean, that must significantly speed up the training process.
It does, and they emphasize that this compression doesn't sacrifice any geometric detail. It's all about representing the information more efficiently. Plus, as a bonus, it leads to a much smaller vocabulary size for the model.
Right, because you have fewer unique tokens to deal with. And the paper does mention that this smaller vocabulary contributes to faster and more stable training.
Exactly. And they've actually done a detailed comparison with other tokenization methods in Table 2 of the paper. When you look at things like compression ratio and vocabulary size, DeepMesh comes out on top, especially when you're dealing with high-resolution meshes. They even show how this translates to faster training times in Figure 10.
Okay, so they've revolutionized how a 3D mesh is represented for a machine learning model, making the whole pre-training process much more efficient. But the paper also emphasizes the importance of their data curation strategy. Why is that so important?
You know, it's like the old saying, garbage in, garbage out. If you train your model on bad data, you're going to get a bad model.
Makes sense. So what did they do to ensure they were feeding their model a healthy diet of high-quality meshes?
They went through this really rigorous four-stage filtering process. It's described in detail in section B.1 of the supplementary materials if you're interested in the nitty-gritty.
I'll take your word for it, but give us the high-level overview.
They get rid of any meshes that are just tiny, like little fragments or incomplete shapes. Basically, anything with a very small surface area is out.
So step one, eliminate the crumbs.
Exactly. Then they take a subset of their data that they consider to be high quality and use it to pre-train a basic deep mesh model.
Okay, sort of test run with the good stuff.
Yeah, you could say that. And they use this pre-trained model to evaluate the rest of the data. If the model struggles to reconstruct a mesh, that's a red flag. It means the mesh might be low quality or too complex for this stage.
Interesting. So they're using their own model as a quality control tool.
Precisely. But they don't just discard everything the model struggles with. They also have this aesthetic assessment step. They render images of the questionable meshes and use another AI model to judge how visually appealing they are.
Oh, wow. So they're incorporating an AI art critic into the mix.
Exactly. It's all about making sure they don't accidentally throw out any complex meshes that might actually be quite beautiful and useful.
That's clever. So what's the final verdict? How much data did they end up with after all this filtering?
They started with 800,000 meshes and ended up with around 500,000.
Okay, so a significant reduction, but still a massive data set.
Yeah, and importantly, a much cleaner data set. Figure 3 in the paper shows the distribution of face counts in their curated data, and it definitely spews towards more well-defined geometries.
And they also showed how this impacts the training process in Figure 11, right? A much smoother loss curve, indicating a more stable learning process.
Exactly. It's all about setting up the model for success.
Okay, so we've got this efficient tokenization, we've got our carefully curated training data. But even with all that, generating complex, high-detail meshes will still result in pretty long sequences. How did DeepMesh handle that during pre-training?
Well, they used a common technique called truncated training. Instead of trying to process the entire super long sequence at once, they broke it down into smaller, fixed size windows.
Okay, so like reading a really long book chapter by chapter.
That's a good analogy. And then they train the model on each of these windows sequentially. Sometimes they even use a sliding mechanism where the window moves across the entire sequence step by step, kind of like a sliding window.
Right, so the model gets to see the whole sequence eventually, but in smaller, more manageable chunks.
Yeah, that's the idea. And to make this process even more efficient, they do this thing called data packaging. Essentially, they group together meshes that have a similar number of faces within each training batch.
Okay, so it's like organizing your laundry before you do a load. You put all the similar items together.
Exactly. And this helps to improve efficiency in a couple of ways. First, it leads to better load balancing across the processing units, like your GPUs.
Right, so you don't have one GPU working overtime while the others are slacking off.
Yeah. And second, it reduces redundant computation. Because if you have a bunch of meshes with similar sequence lengths in a batch, you can process them more efficiently.
Okay, so it's all about optimizing the workflow.
Precisely. And the impressive thing is, with all these innovations, they were able to pre-train models with up to 1 billion parameters.
1 billion parameters. That's mind-boggling.
It is, and it really speaks to the effectiveness of their efficiency-focused approach. They list the details of their model architectures and training parameters in Table 3 of the paper.
Okay, so we've got this powerful pre-trained model capable of learning the basic structure of 3D meshes. But remember, the ultimate goal is to generate meshes that not only look geometrically correct, but also have that artistic quality, that clean topology that a human artist would create. How did DeepMesh achieve that?
That's where their second big innovation comes in. They're one of the first to apply direct preference optimization, or DPO, to the world of 3D mesh generation. They even highlight it in section 2.3 of the paper.
DPO. I'm not super familiar with that. Why is it such a big deal in this context?
Well, traditionally, to make AI models align with human preferences, you'd use something called reinforcement learning from human feedback, or RLHF. And RLHF is a bit of a two-step process. First, you have to train a separate reward model that tries to predict how a human would rate a generated output.
Okay, so it's like training a separate AI to mimic human judgment.
Yeah, exactly. And then you use reinforcement learning to further train your main model to maximize this predicted reward. But DPO takes a more direct approach. It skips the whole reward model thing and learns directly from paired comparisons of generated samples.
So instead of trying to guess what a human would like, it just learns from actual human preferences.
Precisely. It's like showing the model two meshes and saying, hey, humans prefer this one. And then the model adjusts its parameters to make generating the preferred option more likely.
That does sound much more straightforward. And they mentioned that DeepMesh is one of the first to use this technique for 3D meshes, right?
Yeah, it's pretty cutting edge stuff.
Okay, so they've got this DPO thing figured out, but how do they actually gather human feedback on these meshes? What criteria did they use to determine which mesh was better?
Well, they realized that to achieve that artist-like quality, you need to excel in two areas: geometric integrity and visual appeal.
Okay, so the mesh needs to accurately represent the shape, but it also needs to look good.
Precisely. So for the geometric part, they use a standard metric called chamfer distance. Basically, it measures how similar two 3D shapes are. The lower the distance, the better the match.
Makes sense. And what about the visual appeal part? How do you measure something as subjective as that?
They brought in human volunteers. They showed them pairs of messes and simply asked, which one do you prefer?
So they went straight to the source, no fancy algorithms or anything.
Yeah, because sometimes the human eye is the best judge.
Okay, so they're getting both the objective, quantitative data from the chamfer distance and the subjective, qualitative feedback from humans. How did they use this to create the training data for DPO?
They had this really careful preference pair construction process. So for each input point cloud, their model would generate two different mesh outputs.
Okay.
Then they would do an initial filter based on the chamber distance. Any mesh that was way off geometrically was automatically eliminated.
So they set a quality bar for the geometry first.
Exactly. And if both meshes passed that check, or if one was clearly superior geometrically, then those pairs would be shown to the human evaluators for the aesthetic comparison.
So the humans got to see the meshes that had already passed the basic geometry test.
Right. And then the volunteers would simply say which mesh they preferred visually. And this whole process allowed them to create a data set of paired examples where one mesh was explicitly preferred over the other, either because of its geometry or its visual appeal. They show some examples of these preference pairs in figure 4 of the paper, and you can really see the subtle differences that the humans picked up on.
Interesting. And how many of these preference pairs did they collect?
They managed to get around 5,000.
5,000 pairs? That's a pretty solid amount of data to learn from. So once they had all this labeled data, how did they actually use it to fine-tune their model with DPO?
Well, the basic idea of DPO, which they nicely summarize in equation 1, is to adjust the model's parameters to make it more likely to generate the preferred samples and less likely to generate the dispreferred ones.
Okay, so it's all about reinforcing the good and discouraging the bad.
Exactly. So they used those 5,000 preference pairs to fine-tune their pre-trained DeepMesh model using the DPO loss function. And this essentially taught the model to directly produce outputs that were aligned with both the objective geometric metrics and the subjective aesthetic preferences of the human evaluators.
So it's like giving the model a crash course in human aesthetics. And they still use truncated training during this fine-tuning process, right?
Yeah, because even though they were dealing with preferences now, the sequences could still be pretty long.
Makes sense. And did this DPO training actually make a difference? Did it improve the quality of the generated meshes?
Oh, absolutely. In Figure 8, they show a visual comparison between models trained with and without DPO, and you can clearly see that the DPO versions produce much more visual appealing meshes with cleaner topology and more artist-like structures.
So it's not just a theoretical improvement, it actually translates to better results.
Exactly. And they also provide quantitative evidence in Table 1. Their model trained with DPO, which they label as hours WDPO, scored the highest in terms of user preference.
Okay, so DPO is a clear winner. Now, I'm curious about the architecture of the deep mesh model itself. What are the key components that make it tick?
Well, at its core, it's an autoregressive transformer architecture. And each layer in this transformer has these self-attention and cross-attention mechanisms, along with a feed-forward network.
Okay, lots of attention going on in there. And what about the input data? How does it handle the point cloud that represents the 3D shape?
They use a jointly trained perceiver encoder for that. It's based on a model called Michelangelo.
Michelangelo, like the artist.
Exactly. It's a pretty powerful architecture for extracting meaningful features from point cloud data. And those features are then fed into the transformer network through the cross-attention layers, so the model can generate the mesh sequence based on the input geometry.
So it's like the perceiver encoder translates the point cloud into a language the transformer can understand.
Yeah, it's a good way to think about it. And to handle the computational challenges of dealing with long sequences and large models, they also incorporate the hourglass transformer architecture.
Hourglass transformer. Tell me more about that.
Well, it's a specialized type of transformer that's designed to be more memory efficient. They explain it in section 3.2.3 in appendix B.4. And apparently it can save you about 50% in memory usage compared to a standard transformer.
Wow, 50% is huge. That must make a big difference when you're training these massive models.
It does, and they were able to train models with up to 1 billion parameters, so memory efficiency is crucial.
Okay, so they've got all these clever architectural tricks up their sleeve. But at the end of the day, how did deep mesh actually perform compared to other state-of-the-art methods?
Well, the results are pretty impressive. Across the board, DeepMesh outperformed the other methods they compared against, like Mesh Anything V2 and BPT.
In what ways?
Well, in terms of geometric accuracy, they used metrics like chamfer distance and Hausdorff distance, which are all nicely summarized in Table 1. And DeepMesh consistently came out on top.
So it's good at getting the shape right.
Yeah, but more importantly, it also scored much higher in terms of visual quality. They have both the user preference scores in Table 1 and some nice visual comparisons in Figure 5.
And what about the level of detail? Could deep mesh generate intricate meshes with fine features?
Oh, definitely. Figure 5 shows some examples, and you can see that deep mesh captures much finer details than the other methods. It also shows a lot of diversity in its outputs. In Figure 7, they show how it can generate multiple different yet plausible meshes from the same input point cloud.
So it's not just accurate, it's also creative.
Exactly. And they even did some initial experiments with image conditioned mesh generation, which they show in Figure 6. The results look promising.
Image conditioned, so you could give it a picture and it would try to create a 3D mesh based on that.
Yeah, it's pretty cool stuff.
So it sounds like deep mesh is a real game changer in the world of 3D mesh generation. But every research paper has its limitations. What are some of the things deep mesh still struggles with, and what directions do the authors suggest for future work?
Yeah, they're pretty upfront about the limitations in Section D of the paper. One thing they mention is that the quality of the output still depends, to some extent, on the quality of the input point cloud.
Right, so if you give it a bad point cloud, you're not going to get a great mesh.
Exactly. And they suggest that future research could focus on improving the point cloud encoder to make it more robust to noisy or incomplete data.
Okay, so better input handling is on the to-do list. What else?
They also acknowledge that their training data set, while large, could be even bigger and more diverse.
Yeah, more data is always good in machine learning.
Exactly. And finally, they mentioned that their current model size was limited by the computational resources they had available. They believe that scaling up the model even further, adding more parameters, could lead to even better results.
So bigger and better models are on the horizon.
It seems so.
So as we wrap up our deep dive into deep mesh, I think there's a really interesting takeaway here for you, the learner. We've seen how these researchers have managed to incorporate human preferences, something very subjective, into this very technical geometric task of generating 3D meshes. And it makes you wonder, how could this approach, this idea of directly learning from human feedback, be applied to other areas of AI? What other creative tasks could benefit from this kind of human-in-the-loop learning? It's a fascinating question to ponder.
It is, and it really highlights the potential of combining human expertise with the power of AI. Who knows what amazing things we could create together?